lesson 2, so 4.2, maximum values. Again, the highest point on this graph that's given to us is 7.6. We call that an absolute maximum. The lowest point in that graph is 2.1. We call that an absolute minimum. Okay, and then let's go to this. In general, a function f has an absolute maximum at c. C just stands for constant. That's a number, so don't be confused by that. And that just means if f of c is bigger than all of everything else. That's what that stands for, the greater than or equal to. So if f of c, so f of c is the x you plug in to get your max or min, is the biggest possible output. That would be a maximum value. Conversely, the same thing for the minimums here, f of c. Okay, and then notice, this is what I was talking about the local min. On that last picture, if we notice that we restrict the interval from 2 to 5 instead of all the way across what it was. So let's go back real quick. So instead of from 2 to 9, we can restrict from 2 to 9. This is our cutoff. Okay, that max of 4, 5 in that little piece there is called a localized, your local maximum. Okay, that's what this is talking about here. So if we restrict our attention to interval 2 to 5, the largest value is now 4, 5. For that reason, we say that 4, 5 is a local maximum value. Likewise, 5, 3 is the new local minimum, because the smallest value we consider in our given constraints. Okay. All right. So just thinking about x squared. Okay. If x squared, we know what x squared looks like. That's just a simple parabola. Okay. So looking at that, it says 0, 0 is the absolute and local minimum, but this function has no maximum. So it's telling me the answer. We're just talking about x squared. So let's understand that. Why is there no maximum? It just keeps going up to the left and up to the right. There's no fold over. Okay. I only have a valley. Okay. And so this is my absolute min. Okay, and what they're saying in this case, absolute min and local min mean the same thing, but a local min could be something like in the other graph we cut things off. But the point is that this right here does not yield any maximum. Okay, it has no maximum because it does not change direction. Now, if we think about this in terms of remember our testing we did yesterday, increasing, decreasing? If we did that for this graph, what would from negative infinity to 0 be? It would become decreased, and then from after that would be increased. So if you decrease to increase, what's that going to be? That's going to be a minimum, right? Because you're coming down to something, and then you're coming up after it. That'd be a minimum. Now, if I increased, then decreased, that's your maximum type of thing you're looking for. Okay, yeah.
What if they ask you for like a portion not including
not including what's there? You can be none. You would just say there is no local min or max. So if they said, that's a very good question. If they said for x less than 0, then you could not, there would be nothing. You can't look at 0, so it's not included, right? Then it would just be none. It'd have no max or min. For that example. Good question. Okay. Next one we'll look at real quick, looking at just a regular cubic graph. Okay. Y equals x cubed. Now you look at y equals x cubed, it states here in example 2, we see from the graph the function x cubed, there's no absolute local max or min value. Because x cubed is just slowly what the whole time? Yeah, it's just slowly increasing the whole time. It never flattens out. It never gets a slope of 0 with the derivative. Okay? It never gets a slope of 0 with the derivative. Okay? Okay, and you could also say because if we did get a slope of 0, it's right here, but it goes increasing and increasing. Since it goes increasing, increasing, it doesn't have that hill. It doesn't go increasing to decreasing. Okay? Very good. Now the next one we're going to look at is going to have some restrictions. Okay, questions yet? If I'm going too fast, let me know if you're drawing the pictures.
order for it
one turn.
One like x squared in it, basically. Like it has to have more than one variable. Or no?
Oh, you mean it has to turn? No, not necessarily. Not necessarily. And we'll get to that. And actually, there's going to be a lot of instances where we're going to find critical points where we would believe that that could be a turn, and it won't be, and we have to check. So that's part of the game. So, okay, example 3. Function 1 minus x squared, but between 0 included and 1. Has a maximum value 0, 1, but it has no minimum value. It takes on values very close to 0, but it's never actually attains the value 0. Why? And it never attains the value 0. Let's look here. So if I go 1 minus x squared, 1 minus x squared starts like right here, and then it's a minus x squared, so it's a downward parabola, right? But I only want it between 0 and 1, so I want it between here and then here, but not including that spot there. So all this picture is going to look like is this: solid dot, open dot. That's all that is right there. That's 1 minus x squared between 0 and 1, 1 not included. Does that make sense? Yep. Close. We're gonna get to it. Okay. So it does have a max, like it states, at 0, 1, because 0, 1's included. But it does not have a min because 2 reasons. This dot's not included, so we don't have a value. Like, it could get really, really close, but it's not included, so we can't say it has a min. Also, we know with the behavior of this graph that it keeps going. So that means that we can't call a min at all. There's no min value because we know that that graph would just keep going down. Now, if it was solid dot, then we could go ahead and call it a min because we're cutting it off there and including that dot. So it's not a min here because we're not including it. Okay? Negative x squared, right. Negative x squared is a downwards parabola. Right, that'd be a local maximum, yep. Local max, and actually with this one it is an absolute maximum because this is the top, the vertex of that parabola. Good questions, good questions. This like beginning part, I think once we get to the actual examples where we're taking the derivative stuff, it'll make more sense. Right now they're being very basic and just trying to get you to visualize what max and min is. Okay, so if you have, like, if I'm saying anything wrong or if you don't understand something, just speak up. But this is kind of the introductory part, so we're kind of flying through these slides first. Okay, can I go? Okay, so then example 4, the graph of the function x cubed minus 3x. And they want you to look at greater than or equal to negative root 3. Okay? So there's a couple things I want you to understand. Let's look at the regular graph here. So if I just did the regular graph, just what the regular graph picture looks like, I like to go ahead and factor this. That'd give me x squared minus 3. Okay? So could you guys graph the zeros of this graph based on what I just did there? What's the zeros of just the regular graph, not the derivative? 0 and positive negative root 3, correct? So I'm going to put negative root 3 right here, positive root 3 right here, and then we know 0 is right there. So we know our regular graph is going to cross at these points. That's something that I'm going to tell you it's expected to be common knowledge. I hope that you could do that. Okay? Okay, now with that being said, we are going to go ahead and look, and the reason I did that is because that's where this comes from. It wants us to be bigger than that. So I know it's crossing here, so whatever my graph does, whether it goes like this, it's going to start here and to the right only, because it's greater than. Nothing to the left is going to matter. Okay? So now what we're going to do is take the derivative of that. So what's the derivative of f of x? 3x squared minus 3. Can we GCF that? Pull out a 3. Now what's that? Difference of squares. X plus 1, x minus 1. Now we know, and we just said that, the critical values for our derivative is when it's equal to 0, because that's the slope of 0, that's a change of direction. Okay? So then what is our critical points? What makes this 0 now? 1 and negative 1. Good. Those are my critical points, critical numbers. So we know here at -1 and +1, something's happening. So what we're going to do is we're going to take those and we're going to plug them in and see what they give us. If I plug in a 1, what's 1 into the original? What does that give me? Nope. 1, yes, 1 minus 3, correct? -2. And then -1 gets me -1 cubed is a -1 plus 3 is 2. So you can see the graph looks like this. This is how we're getting good at curve sketching. We just create enough information that we could draw that graph. Okay, so now what did they ask for? I think they asked for all of it, didn't they? So we have a local max at where? Good. Okay, and we have a local min at 1, -2. Now the reason these are local, is because this graph, if it keeps going, this keeps going up forever. So like the number, like the whole, like this thing just keeps going up forever, so the y's just keep going. But this is a localized maximum because it's at a certain spot, it's the top of a hill. Okay, certain spots at the bottom of the hill. I know we cut this one off, so this one actually could be our absolute, I believe. Okay, but don't worry about the absolute local stuff as much. It's more just finding the maximum value by where the turns are. Yeah, so I explained that right, sorry. So this is the local max because we can keep going forever this way, and the values of y keep going forever up this way. This is actually the local and absolute min because we cut this off, so this part doesn't happen. Okay? So this one is the local and absolute. This is just local. Okay? All right, here we go. All right, so don't worry about writing this down. This is just a summary. All this summary is just talking about, this is just telling you that the derivative set equal to 0 gives you the change of direction. That's all this is saying. Okay? You want me to read it to you? Okay? So, conversely, that gives us Fermat's theorem. So Fermat's theorem says that f has a local max or min at c if the prime, so doing the derivative, is equal to 0. So all it's saying is that when you take the derivative and set equal to 0, or you take the derivative and it does not exist, those are critical numbers that could be a max or min. Key word in what I just said is could. It could be a max or min. You have to test to figure out if it is or not. So Fermat's theorem is just exactly what we've been talking about. You take the derivative, set it equal to 0. And the next three examples I think are going to be a little bit more. This is saying that when you take the derivative of the function and set equal to 0, those are the critical points that you'll use to find the max or min. That's like our 1 and -1 in the last problem. And it's when it's when it's set to 0, or if you get a do not exist example. So that'd be if you have some type of fraction. So if something that makes 0 on the bottom would be a D and E, that's still a critical point. So I guess the best summary, let me say it one more time, is take the derivative of the function. Anytime you can make it a D and E or a 0 is a critical point that you're going to test by Fermat's theorem. Okay, and then this talks about what a critical number is. So it says we must be careful when using Fermat's theorem, f prime of c equals 0. It does not automatically follow that f has a max or min. So it doesn't mean for sure it's a max or min. For instance, the function x cubed, considered, has no maximum, yet f prime is 3x squared. So by our making that a 0, 3x squared would be 0, 0, but that wasn't a max. Okay? The significance of the derivative being 0 is just a tangent to the horizontal. That's what we're talking about. The 0 is the part where it changes direction. But it does not necessarily mean it's a max or min. Okay, we need to use critical numbers. Okay, a critical number of function is a number c in the domain of f such that f prime of c equals 0 or f prime of c does not exist. Those are what we test. That was our 1 and -1. Those are considered critical numbers. So a critical number is anytime your derivative equal to 0 makes it equal to 0 or does not exist. No, that's fine. All right, so example 5. So this one says just find the critical numbers. Okay, there's two questions. There's A and there's B. So we'll do A first. So to find the critical numbers, the first thing is we still have to take the derivative. Okay, so we are going to go f prime of x, I'm doing part A right now, is 3x squared plus 12x plus 9. Okay, I want to set that equal to 0. And I also want to factor, or try to get this simpler so I can see what makes it 0. So I'm going to pull a 3 out. That's now factorable. So my critical numbers for this example, that's all it's asking for right now, is -3 and -1. Those are my critical numbers for part A. Any questions on that? Nope, because there's no x here. Yep, just factored it. What's that? I took the derivative. That's what this is. Yeah, I took the derivative here, and then I took a 3 out, and then I factored. Okay, with part B, we have an absolute value here. So for the absolute value, first off, what do we know about, remember when we talked about in the very beginning, you can only take derivatives of like sloped lines, and we talked about how corners you can't. So, and absolute values have corners. And so what happens is that 0, it's a critical point, but does not exist because we can't take a derivative of a corner. Okay, I know it kind of sounds weird, but let me kind of write down the concept here. So if we do f of x, so we're looking when x, it's x when x is greater than 0. That's the absolute value definition. That whatever you put in for x when x is greater than 0 is just x, like 4 is 4. Okay, but it's opposite x whenever you put in something less than 0, because it's absolute value. So if I put a -4, it's going to be a +4, right? Just the opposite idea. So with that being said, if I take the derivative of these two, I get x, what's the derivative of x? 1, so I get 1 for greater than 0. Oh, I keep writing it wrong, I'm getting confused, sorry. 1 for x greater than 0. And then what's the derivative of -x? Now this is, I think this is kind of cool because what do those represent?
Critical points.
No, not critical points. Remember this is the most confusing topic about absolute value. What's the slope of this half? What's the slope of this half? That's where those come from. When x is less than 0, the slope was -1. When x is bigger than 0, it's +1.
I'm confused. I don't understand what we just did.
So, go ahead, Emily. Let's see what your question is. This part? Because absolute value, and this might answer your question too, absolute value comes from, we know there's two types. There's a negative number and a positive number. So the positive x kicks out a positive x. So if I put in 4, I get 4. If I put in a negative x, if I put in like a -2, I get the opposite of -2, which would just be +2. Yeah, so this is like a definition of an absolute value. So this is saying, again, if I put in a negative number, I get the opposite of that negative number. If I put in a positive number, I get that positive number. That's just your absolute value rule. Okay, and then what we did was we took the derivative. Derivative of x is 1. Derivative of negative x is -1. That's the slope of those lines. Now, we don't include 0 on this because I told you the corners we can't do the derivative of. So really, we can't say there's a local min or max on this when we get to that. We'll get to it later. But for now, the point is just understanding that that derivative yields those slopes. Yeah, for that one, yeah.
What if there were other values?
We'll get to that in a different day. Okay. I think the absolute value, they just talked about this so you didn't forget about that being there, because we have talked about the corners and stuff, and that's kind of the basis of what they want to talk about there. So 0 still is a critical number, like you said, because that's still what makes this 0. Either one of them, it's still what makes them 0 is just x. So don't forget that, but it's okay. All right, so here's the procedure for finding the absolute max and min. This is in your book. If you don't want to write it down now, you don't have to, but it is in your book. So the first thing you want to do is you find your critical numbers, which we learned how to do. Second thing you want to do is also look at the endpoints. So if they give you endpoints, those count as critical points. So you might want to highlight that. So if they say you have to be between 3 and 6, 3 and 6 are going to be points you're going to test for your max and min. We're going to do it in a second. And then 3, the largest values, so whatever your outputs, the largest outputs are your maxes, okay? And the smallest outputs are your minimums. The endpoints are like the restrictions that could give you that inequality. Those will be your endpoints. Yeah, essentially. But yes and no. Again, I'm probably not going to be too picky on local or absolute. If you just say this is a max or min, I'll probably be fine with it. You sure? We only have 2 examples left, and I'll go back to it. Okay, find the absolute max and min values of this function. So this is what I'm talking about. I'll go back. We can go back. Just pause it for a second. So -3.5 and 1 are my endpoints. That's what I was talking about, endpoints. And then what we need to do now is figure out the critical points of this function. Okay, so we're going to find the critical points. So critical points come from your f prime. Okay, 3x squared plus 12x. That's the one we already did. Pull the 3 out again. And that factored. So my critical numbers are -1 and -3. Okay, and so now the last part, which is kind of the easy part, you just plug all of those in. You plug in f of -3 to the original, f of -1, f of your endpoints, and f of 1. You plug these into the original and see what the outputs are. Okay, when I plug in -3, I get 2. When I plug in -1, I get -2. When I plug in -3.5, I get 1.125. When I plug in 1, I get 18. So then right there, what is my max and what is my min? 18 is the max, so 1, 18, absolute max, or just max, whichever. Okay, and then my min, -1, -2. And that's it. Okay, if you forgot where -3.5 and 1 came from, they are the endpoints that are given to you in the problem. So no work required there. You just have to test them to see if they end up being a max or min. And that's because they're both included, right? So whatever this graph looks like, okay, we know 118, so whatever, we have 118 up here. -1, -2 is down here. That's weird. Anyways, so it could be, it stops right here, so it could be something like that. So here's my min, here's my max for that given constraint, just depending on what it is. And one of them happens to be the endpoint. Okay, and last example, and then I'll go back to that page you guys need more of. Okay, so find the absolute max and min of this one. So this one you could use product rule right away if you wanted, or you can distribute that x to 2/3 in. For my notes, I distributed it in. So I made it this, 5x to the 2/3 plus x to the 2/3 plus 1 is 5/3. Okay, I distribute that x in. And now I'm going to take the derivative. Okay, derivative of this, drop the 2/3. That's going to give me 2 times 5 is 10 over 3. That's now, when I take the derivative of 2/3, it's going to be a what? Drop the 2/3. 5 times 2/3 is 10/3. Because that's derivative, right? You drop the exponent. Okay, so 10/3, x to the 1/3 on bottom because it's negative 1/3. That's what I wanted. So I was trying to get you to say. Or you could leave it up top negative, whichever you want to do. I think I actually left it up top negative, but it's okay. Okay, and then this one would be 5/3 x to the 2/3. So I'm actually going to write that as a negative. I think it's easier to see this way what you should do next, and we'll see if you guys can tell me what you think we should do. What should we do next? What's that? Just kind of want to see if it'll help you see what we should do next. And sorry, it's negative, sorry. We can't add them because they're different exponents still. Yeah, we want to pull out the smallest x. The smallest x is x to the negative 1/3. So if I pull that out, okay, that makes, we'll keep what's in there for right now, and we'll take something else out if we can. I get 10/3. If you take a negative out, you're really adding, what's 2/3 plus 1/3? Yeah, 3/3. So then you get plus 5/3 x. So now this helps us find our critical values. You could take out a third if you want, but you can still see it. Okay, what does that x have to be to make that be a negative 10/3? Negative 2. So one critical number is negative 2. What's the other one? 0. And this one's kind of tricky. It still is 1, but where's this really? It's down here really, right? So being on bottom is not necessarily the 0, it's a D and E, which is still part of Fermat. So it still works. I'm just telling you that it's not a 0, it's a D and E. Yep.
You know how when we factored out into, I think we can factor one nicely,
Yeah.
then your critical point is the opposite
Yeah.
of x, why is it not positive 2 then?
For, wait, so here?
Yeah, like I get the negative 2 and
Because if I put a positive 2,
wait, never mind.
yeah.
Never mind.
Yes, it's a plus. Okay. Okay, so that's my critical numbers. Find the absolute max and min. So what do I want to do now? I have my critical numbers. Yeah, sub them in. So I sub in though. What am I subbing in though? F of negative 2, F of 0, F of negative 5, and F of 1. Okay, so sub those in. Actually, didn't write those ones down, unfortunately. So let's see. If I can just, we can do it real quick. Whoever's got a calculator, anybody got a calculator? Yeah, Garvey, you want to do the first one? Second one should be easy. Dar, you want to do the third one? You do the fourth one. So then 0 should just be 0. probably going to be a decimal most likely. Well, this person, who's the third one? Which one were you doing, do you know?
I'm doing a lot of.
Oh, yeah. So, Dars, you should be 0.
Oh, wait, I did the first one,
Oh, yeah, I guess.
sorry.
Which one did you do? Okay, so what'd you get?
My fault. Yeah, this is.
The third one's 0. What's that? Okay. Okay, and then 1?
I got 6, but I don't know if that's right.
Yeah, that's right. Because 5 plus 1 is 6, and then 1 cubed and then square rooted is still 1. 6 times 1. So, what's our max?
1, 6.
Okay, good. And we got 0 twice. Okay, so those are going to be our local mins, or we'll have 2 minimums. So the same spot, 0, 0, and negative 5, 0. So the same, that's okay. Okay. All right.